right, my friends, welcome to section 3.5. This video will be about part 1, and section 3.5 is all about derivatives of trig functions. Okay, a little warm up for you. First warm up. Expand each expression. Using the appropriate sum formula. And for part A on this warm-up, let's have you see if you can remember how to expand sine of the quantity u plus v. And then for part B, let's do basically the same thing, but with cosine. All right, my friends. And then warm-up 2 is simply to evaluate each limit. And a hint for this, just so that you don't spend too much time on it, you may want to use your calculator. Okay, so for part A here, we'll do the limit as x approaches 0 of the sine of x over x. And then for part B, let's have you look at the limit as x approaches 0 of cosine of x minus 1 over x. Okay. So please do pause the video and do your own discovery on these so that you can have your own, so you can feel satisfied with the results as opposed to just trying to choke down what I tell you the answers are. Those two experiences will feel very different. So, okay. So assuming that you've done so, let's go ahead and check to see what you put for the expansion of sine of the quantity u plus v. So this is a matter of recalling the sum formula for sine. So this should equal the sine of the first angle times the cosine of the second angle plus the sine of the second angle times the cosine of the first angle, or something that's equivalent to this. Remember, addition and multiplication are commutative, so there are a couple different versions of this answer that's equivalent. Now for the sum formula for cosine, it's the cosine of the quantity u plus v would be cosine of your first angle times cosine of your second angle minus sine of your first angle times sine of your first angle, and then times sine of your second angle. So notice that a common mistake for the sum formula for cosine is people want to put a plus there, or all sorts of stuff like that. So just kind of watch out. So okay, let's see. Now that we've got that taken care of, let's look at evaluating each limit. The limit as x approaches 0 of sine of x over x. First thing, I don't know that since x is approaching 0, it probably doesn't matter too much, but usually when it's trig, I really like making sure that I'm in radians mode. And then we could do this graphically, we could do, we could graph sine. Actually, let's do it this way. Let's do, I guess, the quantity sine of x divided by x. I might have some unnecessary parentheses there, but that's okay. And then let's do a window of maybe like negative 10 to 10. I'm going to do zoom fit. That's my favorite. The calculator just kind of guesses what you want to see. Okay, so here's what the graph looks like, and then let's look and see what happens when x values get really close to 0 on either side. So we could do, let's see, what would be a good choice here. Actually, let's just do, sorry, let's just do trace and see if that'll do it for you. So, so you can see when we're really close on the right side to 0, you're getting really close to a y value of 1. When you're at 0, the graph is, the function rule is undefined. And then when you're on the left side, you are very close to 1. So hopefully we're okay with saying the answer is 1 here. If you don't feel satisfied, like if that's not close enough to 1 for you, you could always, let's see, let's play with this. Let's do zoom box. You could always just kind of like highlight that area a little bit. Actually, sorry, let's control the window a little. Let's do a little bit higher than 1, like 1.1, first of all. There we go. It's pretty clear it's 1, but I'll quickly demonstrate first how horrible I am at pushing buttons. But anyway, you could do what's called zoom box. So when you push zoom box, the first time you push enter, it'll make one of the corners of the box, and then when you push enter it again, it will fill the entire screen with whatever you have boxed in. So there we go. If you weren't sure it was 1 before, you'd probably be pretty sure it's 1 now. And then now if you were to do trace, you'd probably feel a little more satisfied with how close you're getting to 1 here on both sides. There we go. All right, my friends, the answer is 1 there. That's the point. Anyway, and then let's look at the second one. Limit as x is still approaching 0, but this time of cosine x minus 1. And then graph it. Oh, I'm not going to like my window at all for this one, so let me reestablish the window. Let's start out with -10 to 10, and then we'll do zoom fit. Okay, here we go. So here's what the graph looks like. All right, my friends, it looks like it's approaching 0 on both sides to me. It's most likely undefined right at 0, but it looks like the limit value is 0. All right, my friends, I hope this helps. Okay, now for example 1. Okay, for example 1, we'll do this in a couple parts. Part A, let's have you graph f of x equals sine of x. And when you do this, let's do our best. We're going to do this by hand. Let's do our best to have what's called a square scale, something that we don't normally have when we graph sine. And so let me show you what I mean by this. Oh, that's a bad start. All right. Oh dear. Okay. Anyway, pretend this looks super nice. Okay, so here is a really sad XY plane. So let me demonstrate kind of what we usually do, and then I'm going to talk with you about why it's super not a square scale. So like typically we would make tick marks with pi over 2, and then I have a tendency to make like 1 and -1. So this is not a square scale if you go about it like this. So because pi is about 3.14, divide by 2, you've got about something a little bigger than 1.5 units sort of this way. But then you have 1 unit being this huge jump. So this is 1.5, but yeah, this is 1. So to fix that, I think I'll probably make these a little wider apart. So like this is pi over 2, pi, 3 pi over 2, and then 2 pi. And then since this would be about 1.5, maybe 1 would be about here. So if you have the spacing be like this, then you're looking at something that's a little more of a square scale. like so. Okay, sort of. Something like that. Okay. Okay, so let's graph sine on it. And this is something that hopefully feels easy for you at this point. So sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, sine of 2 pi is 0, and then sine of negative pi over 2, negative pi, and negative 3 pi over 2. And then let's just fill in the sine wave. Like so. Okay, so that's part A, just to graph it. Now for part B, I'm going to ask you to use your graph from part A to complete this given table of values. So here we go. Okay, so let's see. Okay, so let's start with that. Okay, so let's say that I ask you, basically what I'm asking you here is what is f prime of 2? So let me just make sure that everybody's clear on that. I want to know if x is pi over 2, what's f prime, basically, at pi over 2. So what we're going to do here is we're going to draw upon the graphical explanation of what f prime means. And remember, way, way, way back, f prime meant the slope of a tangent line at a certain place. And so I hope it makes sense. F prime of pi over 2 should be the slope of this tangent line right here. And so what would you guys say the slope of the tangent line is at pi over 2? I hope you would say that it's 0. And then let's play with, what if I give you pi? And it's right here, which is why I wanted you to draw this with a kind of a square scale. So at pi, and you can be guessing or approximating at this point, but what would you say the slope of the tangent line to this graph is at pi? And so whatever your guess is, I'm guessing that it's something kind of close to -1. How about 3 pi over 2? If x is 3 pi over 2, what would you say the slope of the tangent line is to this graph there? And I hope it makes sense that we would say the slope is 0. How about 2 pi? So at 2 pi, what would you say the slope of the tangent line is? And I hope whatever you're approximating it to be would be something about 1. And so on. And so we can go ahead and fill in some negative value. Actually, let's do 0. I forgot about 0. So what would you guys say the slope of the tangent line is at 0? I would say probably 1. How about at negative pi over 2? What's the slope of the tangent line? 0. Etc. Okay? So for part C, the reason that I'm asking you this for part B is because for part C, I'm going to ask you to graph, if f of x is sine of x, graph f prime. Oops. I'm going to try making a square scale. So So I have my attempt, at least, at a square scale here. And then let's go ahead and basically plot these points. So according to this t-table, whatever the graph of f prime is, it should have the point pi over 2, 0 on it. And it should have the point pi negative 1 on it. It should have 3 pi over 2, 0, 2 pi 1, 0, 1, negative pi over 2, 0. And then if you want more points of accuracy, you could always go back to the graph at negative pi. The slope of the tangent line looks like negative 1. So that would turn into negative pi negative 1 because I'm graphing the derivative function. At 3, negative 3 pi over 2, it looks like the slope of the tangent line is 0. So I'd plot the point negative 3 pi over 2, 0 because I am graphing what the derivative function would be. So I'm basically showing what this t-table would look like. Now, if you look at these points that we have here for the graph of f prime, I'm sure there are lots of ways you could connect these points, but how many of you are actually quite tempted to fill it in with this? And my friends, this is certainly not a proof, but we can certainly prove this pretty darn soon. But if you fill this in, what does this graph look like? It looks a whole lot like the graph of cosine of x. So what we're getting at here is that if f of x is sine of x, its derivative function is cosine. The derivative of sine is cosine. So we could even go back up here and fill that in, let's move this out of the way. Turns out if f of x is sine of x, then f prime is cosine of x. There we go. All right, and so now let's go ahead and make it official, and then we're going to prove it. So first the formal statement. If you are asked what's the derivative with respect to x of sine of x, the answer, my friends, is cosine of x. Okay, and a proof, a formal proof, this would be a proof based on the definition of derivative, where the function role we're taking the derivative of is sine of x. So we would say, let's prompt our work with d dx of sine of x. And my whole goal is to start out with the definition of derivative, again, where instead of f of x, I have sine of x, and then to show based on that you just get this pretty little cosine of x as your answer. So applying the definition of derivative, where f of x is sine of x, we would have the limit as h approaches 0 of sine of the quantity x plus h minus sine of x all over h. All right, my friends, and now maybe you can see what I was up to in the warm-up when I gave you a sine of the quantity x plus h and asked you to expand it.
Hi, Mama.
Hi, gorgeous. How are you?
No.
No, I don't. So we're going to expand sine of the quantity x plus h using the sum formula for sine. So we'd have sine of x times cosine of h plus sine of h times cosine of x. That's just the expansion for sine of the quantity x plus h. So we're going to bring down minus sine of x. And then it's all over h. All right, my friends, next we are going to kind of regroup this. So what I'm going to do is in the next step, you're going to see me group sine of x times cosine of h with negative sine of x. And then the sine of h cosine x will be by itself. So we would end up with, this would be the same as the limit as h goes to 0 of sine of x times cosine h minus sine of x, as promised. We're going to put these two together, over h. And then plus, you'd have to add in sine of h times cosine of x over h in order for this expression to be equivalent to what you had. Next, if you've been tortured enough with algebra, then you should notice there's a common factor here that we can factor out. So I'm going to rewrite this as the limit as h goes to 0 of the quantity sine of x times cosine of h minus 1 all over h plus, similarly, sort of, I'm going to go ahead and pull the cosine of x out to the side. So this fraction is the same as the cosine of x times sine of h over h.
All the clothes we washed already.
Oh, do you want to have a laundry party later?
No.
Oh, I have to finish this video, Tweety, and then we can do it. Okay? Okay, I'll try to hurry.
I got it out for you now.
Thank you.
I got most of it out.
Okay. We're going to have a laundry party later. All right, anyway, so the next thing that we're going to do is use the properties of limits, and there's so many fun properties of limits. We're about to distribute this limit over addition, so we'd have the limit of the first expression plus the limit of the second expression.
Smell it.
Oh, that smells much better. Yeah, good. All right, sweetie. I gotta make the video, okay? We'll be done in a little bit. All right, so we'll have the limit as h approaches 0 of sine of x times cosine of h minus 1 over h plus the limit as h approaches 0 of cosine of x times sine of h over h. All right, also recall that limits distribute over multiplication, unlike derivatives. Anyway, so we'd have the limit as h goes to 0 of the sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus the limit, I seriously need to start writing smaller, as h goes to 0 of cosine of x times the limit as h goes to 0 of sine of h over h. There we go. Okay. Now let's go ahead and evaluate each limit. The limit as h goes to 0 of sine of x, well, h can do all at once. There's no h in this expression, so sine of x will stay sine of x. So as far as this limit's concerned, sine of x is a constant. Now limit as h goes to 0 of cosine of h minus 1 over h. Now maybe you can see what I was up to in this warm-up right here. I wanted you to have thought this through already. Notice that if all these x's were h's, you would have exactly this expression. So this entire expression goes to 0. So we would have sine of x times 0 plus, similarly as over here, limit as h goes to 0 of cosine of x is just cosine of x. Limit as h goes to 0 sine of h over h, that's what we thought through here, so that is equal to 1. All right, simplify this. Sine of x times 0 is just 0, and so the only thing left standing is cosine of x. And that, my friends, is the formal proof that the derivative with respect to x of sine of x is indeed cosine of x. And we didn't just get lucky with a little graphical reasoning. It really is. All right, my friends. Now let's move on. And so I'm actually going to get example 1 back here because we are going to refer to it. Because if you think about it, we could kind of recycle a little bit. For part C in example 1, we actually did graph the cosine function. So here's the graph of the cosine function. Well, with example 2, we're going to look at, well, what's the derivative of cosine? And this would be a good time for you to kind of think about what you think the answer is going to be. What do you think the derivative of cosine is going to be? And you're probably at least close to the right answer. So for example 2, let's have you refer to example 1, part C, and graph graph, I'm going to rename things a little bit though. So let's say graph g prime of x if g of x is cosine of x. Okay, so basically if this is your original function, cosine of x, we're just going to graph g prime. So, and you can do the t-table if you found that helpful, or you could skip it. I'm going to demonstrate what it looks like to skip it.
But do you have it able to be finding Leo yet?
What, sweetie?
I'm looking for Leo.
I haven't seen him, buddy. I know he's around here somewhere, though.
Me too. Where is he?
I don't know, Tweety.
What?
I don't know, buddy. You look. I have to do this, though, okay? I'm almost done. All right, my friends. Okay, so whatever the graph of g prime is, if this is the graph of g, then we'd want g prime to have a value of 0, since the slope of the tangent line here is 0 at 0. So we'd plot the point 0, 0. G prime at pi over 2 is -1, so we plot the point pi over 2, -1. G prime of pi is 0, so we'd plot the point pi 0. G prime of 3 pi over 2 is 1. G prime of 2 pi is 0. G prime of -pi over 2 is 1. G prime of -pi is 0. G prime of -3 pi over 2 is -1. All right, my friends, let's fill it in and we'll see if this looks like the graph of what you were expecting. And some folks are just a little surprised by this one because a lot of folks were thinking that the derivative of cosine was going to be sine. And the derivative of cosine isn't sine, but it is. If you think about it, the sine wave just got reflected. So it turns out the derivative of cosine is negative sine. So this is something worth memorizing and not forgetting until you and possibly your children are finished with your math career or their math career. So the derivative of cosine, it turns out, is actually negative sine. Okay, and let's prove it. Now, what would be super cool is if you pause the video to see if you can seriously pull this proof off yourself, and then check and see how we compare. I'm going to do a proof a lot like the one we just did for sine, for the derivative of sine being cosine. I'll probably skip a couple steps though. So our prompt is ddx of cosine of x. And according to the definition of derivative, it would be the limit as h goes to 0 of cosine of the quantity x plus h minus cosine of x all over h. Next, we will expand the cosine of the quantity x plus h using the sum formula for cosine. We would get the cosine of x times the cosine of h minus the sine of x times the sine of h. Bring down the minus cosine of x, and it's all over h. Next, a little creative regrouping. We're going to group this term with this term. I'm also going to save myself a step and factor out the cosine of x. So I would have the limit as h goes to 0 of cosine of x times cosine of h minus 1 over h minus, and then we'd still have this term to account for. I'm going to write it like this, sine of x times sine of h, but it would have to be over h. All right, my friends, and I know I skipped a couple steps, but I'm hoping if I showed them in the previous one, you'll kind of forgive me for skipping things here. All right, next, limits distribute over subtraction, and then step right after that, we would show that limits distribute over these multiplication pieces that you have here and here. So I'm going to jump to where we've distributed over everything. So we would have the limit as h approaches 0 of the cosine of x times the limit as h approaches 0 of cosine of h minus 1 over h minus the limit as h approaches 0 of the sine of x times the limit as h approaches 0 of sine of h over h. Okay. If h goes to 0, cosine of x gets to just stay itself, cosine of x. If h goes to 0, cosine of h minus 1 over h, as we discovered in the warm-up, you would get 0. H going to 0 on sine of x leaves you with sine of x. And h going to 0 on sine of h over h leaves you with 1. Simplify this expression, and lo and behold, we have proved that the derivative with respect to x of cosine of x is indeed negative sine of x. There we go. All right, my friends, one example just to demonstrate how you could use this stuff kind of mixed with other things, and then we're done for this video. All right, you should be ready to do the worksheet that goes with it. So example, I think we're on example 3 at this point. Let's say you are given f of x equals, let's say you're given x cubed times the cosine of x. For part A, if I ask you to find f prime of x, what would you do? So we have a saying in calculus, it's diagnose before you treat. So we need to take the derivative of both sides. So let's give this thing its diagnosis before we just get going and doing things. So, so on the right side, notice you have x cubed, which is a function of x, and it's being multiplied by the cosine of x, which is another function of x. So I hope it makes sense that you're going to need the product rule to do this. So you can use the product rule, and then within the product rule, you'll need to know the derivative of cosine. So let's do it. F prime of x would be 1 is x cubed. D2, derivative of cosine, is negative sine, plus 2, which is cosine, D1, which would be 3x squared. There we go. And then after that, you just simplify it. So f prime of x then would be negative x cubed times sine of x plus 3x squared times cosine of x, or anything equivalent. All right, part B, let's have you find the equation of the tangent line to the graph of f at or when x is equal to pi. All right, my friends, so you need the equation of the tangent line. So first let's get the slope of the tangent line. This is a slope formula, so we would just need to plug pi into it to get the slope. So f prime of pi would be, and then you just plug pi in for all the x's. So we'd have negative pi cubed times the sine of pi plus 3 pi squared times the cosine of pi. So what's the sine of pi? That's 0, right? And the cosine of pi, negative 1. So that means f prime of pi would simplify to be, this entire term would go to 0, and then you'd end up with 3 pi squared times negative 1, or negative 3 pi squared. All right, so there's your slope of your tangent line at that. And so now let's get the point of tangency. So the point of tangency, they gave us the x coordinate, we just need the y coordinate. So we're gonna plug pi in to the original function to get the y coordinate. So f of pi would be pi cubed times the cosine of pi. Again, the cosine of pi is negative 1, so you just get negative pi cubed. Now for your answer, they did ask for the equation, so I'm going to demonstrate a point slope form answer. So point slope form, you do y minus your y coordinate equals your slope times x minus your x coordinate of your point of tangency. You're welcome to leave it like this. I think most of us are tremendously bothered by double negatives, so probably writing your answer as y plus pi cubed equaling negative 3 pi squared times x minus pi. And I know some of you are hardcore y equals mx plus b folks, so you are welcome to write your answer in y equals mx plus b. The rest of us slobs are just going to leave our answer like that and be perfectly proud of ourselves. All right, my friends, that is it for section 3.5 part 1. I hope you feel like you can do the worksheet that goes with this without too much trouble at this point, and I hope that you'll ask me questions if you do run into trouble. Take care, everybody.